So Dave, I've heard you actually started as an observer, or you had an observational phase very early on.
That's a gross exaggeration. I
Okay.
had a telescope and I looked at the sky.
Okay. When you're a kid, see, I lived in big cities with clouds and light. I never had a telescope growing up, so you're an observer ahead of me already.
Well, it wasn't due to any great search for skies, but
Mhm.
just they were there
Right. So you had a dark sky. Where did you grow up?
in western Kentucky in
Okay.
farming country. So
Right.
we could see the stars.
Nice. And then but you tilted towards physics and theory and so on. What was your progression?
I was enthralled by a book by Fred Hoyle, Frontiers of Astronomy, in which he tried to explain how stars would evolve and make the elements,
Mhm.
all of the chemical elements.
Right.
And I was hooked.
Yeah, it's one of the big questions
One of the
you can
big
ask about
questions.
nature. Yeah.
Yes. And it's involved not only in that, but also the formation of black holes, which is another big question.
Right.
And now we know a lot more, and there are a lot more exotic objects which we see which are related to this.
Right.
So it's become a very fertile field.
Right. Now, but you moved fairly quickly towards not just the sort of routine protean creation of elements in normal stars, but to these rather more transient, exotic, and dramatic phases of stellar evolution. What was the hook there? That we probably didn't understand them at the time.
I think a lot of boys and girls, too, for that matter, who became interested in stars were fascinated as children with explosions, from firecrackers on up.
So you weren't satisfied with just blowing a thing up or a firecracker. You had a star to worry about.
Right.
Here.
I wanted to see how it worked.
Cool. And what was let's go back to the stages when the theory was not as well developed and computers, of course, were not very capable. What were the challenges early on in developing this field?
Basically, the problem was that you had to be more brilliant than any human to write down exact solutions for three-dimensional time-dependent equations.
Mm-hmm.
It just didn't work. In college, one of my professors, to give us a flavor of what one could do in the future with computers, had us by hand calculate the wave function of the hydrogen atom using finite differences, which is the way that we do it now on computers. By hand, it is very tedious and very slow.
Is that an edifying thing to do or not?
Actually, it's one of those things that you're glad that you've done it.
Right.
I wouldn't do it now, but it gave a tremendous amount of insight into the limitations of using computers.
Mm-hmm.
But I didn't actually have the chance to use a real computer until I was in graduate school.
Mm-hmm.
These were in the days when we didn't have laptops.
Right.
We didn't have printed circuits. The computers at the time were made of vacuum tubes.
Mm-hmm.
And while I was in graduate school, the IBM 7094 came out, which was one of the first transistor computers.
Wow. So theory was still a fairly pure analytic pursuit in those days.
Yes.
And with the strengths and limitations that
Yes.
implies.
Yes.
Yeah. Another question, who were your sort of role models or inspirations? You mentioned Fred Hoyle. I mean, he's a singular character in the history of the field. But I'm wondering, you won the Beta Prize from the American Physical Society. Was he an influence? Was he?
There were several people. Let me do them in order of that I met them. After arriving in New Haven, I decided to be a physicist, and as a thesis advisor, I was lucky enough to be accepted by Al Cameron,
Mm-hmm.
who was one of the pioneers of the synthesis of the elements in stars and
Right.
the theory. And he pushed me directly to learning all the physics that I could and giving me access to computers. And Al had a wonderful style of teaching. He didn't say that this couldn't be done. He took the point of view, see what you can do,
Right.
and cheered us on.
Great. Yeah. So he didn't set limitations on
He
you at all.
didn't set limitations. And with a start like that, I became a postdoc with Willie Fowler, who later won the Nobel Prize
Right.
for doing work in this area.
Right.
And
And Hoyle, some people thought maybe Hoyle was slighted in that.
Fred did not, but Willie was worried about it.
Okay.
Some years later, I organized a conference at Yerkes Observatory. This is when I was on the University of Chicago faculty. And happenstance had it that on the first day of the conference, the Nobel Prize was announced that Willie won.
Wow.
So it was an amazing experience.
Yeah.
And I would say that one of the only sad thing that Willie said the whole day was, I wonder what Fred is going to think.
Right. So Fowler, another amazing figure in the field. Yeah, I remember him telling stories about the train rides they set up for him when he got the Nobel Prize, when they found out he was a mad keen train enthusiast.
Yes. In fact, for his 60th birthday, my wife Betty and I were wandering around London, and we found a working model steam engine. So we mentioned this to Don Clayton, who was also visiting Cambridge at the time. And we took up a collection with the other visitors. So we presented this model to Willie because he was mad about trains, having grown up in Lima, Ohio.
Right. Yeah, that's nice.
So this fitted beautifully.
Yeah. Now, talk a little about something that's a little mystical to people not in science or outside the field, the idea of physical intuition, especially when you're working on problems that are very non-terrestrial, very unfamiliar. How do you develop a sense that what you're doing, whether you're on the right track, that you're or even the right order of magnitude for calculations you're doing or inferences you're drawing?
I think that an important component is unconscious. Time and again, I've worked on a particular issue and gotten to the point where no progress was being made. Then the next morning, just after I get up and start taking my shower, I think of something that is an idea which I couldn't, for the life of me, drag out the previous day. Suddenly it's there.
Right.
And then that makes, you get into the business as usual kind of science then, because you could go from step A to step B to step C and work your way through it. But the idea, which is crucial, because if you don't have the idea, you never know where you're going.
Right.
The idea seems to involve not only the conscious mind, but the unconscious mind.
Right.
Somehow things get organized in there when you've slept on them.
And also there's something like a modulation of, intensely thinking about something and then backing right off. So you're a long time visitor to Aspen and the Center of Physics, and some people again outside might think, well, that's a boondoggle for those physicists and so on, but it's an incredibly productive place, in part because of the intensity of the dialogue and the fact that you can recreate and let that percolation.
And it's not it's no accident that I wrote my most referenced paper there after hiking all morning.
Wow, interesting. Yeah.
Willie Fowler used to say, well, we work very hard, so we get to play very hard.
Right.
I think that part of science is not well understood.
Right.
It, as you say, the boondoggle image, but that isn't at all what it is.
No.
It's a matter of clearing the brain.
Right. Let me ask another question about the sort of physical intuition side about what has happened. So as the computational capabilities have become much better, there's presumably a potential danger of getting detached from that physical intuition. I mean, you can sort of believe your simulations a little too much, or whatever. I mean, it's not quite as simple as it was when the pure theory led the way, if you like.
I think you're right about that, but I'm not so worried that it's a significant danger. And the reason is that anyone who has strong physical intuition will assimilate the results of the computer simulations
Mm-hmm.
and make connections, make the creative leap, and go far beyond what we can do with the computer.
Right.
Remember, the computer is more like an experiment rather than a theory.
Mm-hmm.
Computer is one particular instance. And then the question is, what would have happened if you had changed something? Well, instead of having to each time rerun this complicated program, theory allows you to understand how things work together. So you don't have to do a zillion instances to understand how things work.
Mm-hmm.
You build an intuition, a quantitative numerical theory, which describes computer simulations.
Right.
And then you can go on, and because of the power of the computers, we're now in a position where when we proceed, we can do problems that ordinary mathematics, the sort that was taught in the last century, basically can't handle.
Mm-hmm.
That is, nonlinear systems, chaotic systems, complex interacting systems that we were never able to solve well
Right.
in an analytic way. John von Neumann was the one who first wrote out this dream. That is, he had the notion that you could solve the problem of turbulence by using computers to explicitly calculate the horribly complicated behavior and study those very carefully, and then do mathematics
Mm-hmm.
to have an appropriate theory.
Right. Now, he's another singular figure, someone you knew.
I did not know him. I wish I had. Our world lines didn't cross, although I was at a lot of the places that he had been.
Right. And he had his feet in so many fields, it's amazing. Or in
Yes.
in the starting points of so
Yeah.
many fields.
Well, he and Landau are two people whom I never met, but were really impressed by the breadth of their
Mhm.
knowledge and interests.
Mm-hmm. So let's get to supernovae and maybe just paint a broad brush stroke view of the extreme physical conditions that we're trying to understand in a supernova. Any type. I want to talk about 1As in particular, but just in general terms.
Okay, I worked on both of these at the same time, sort of in parallel.
Mm-hmm.
The 1As are basically enormous firecrackers, except instead of gunpowder, they have thermonuclear burning.
Mm-hmm.
They blow themselves apart. The way that nature manages to make the firecracker is to add mass to a white dwarf star. And eventually, it adds enough mass so that the star becomes less and less able to maintain itself against the gravitational pull. And a little bit more mass gives a bigger shrinkage in the star, and a little more,
Mm-hmm.
so you get to an unstable condition. Before it collapses, the compression makes the inner parts of the star hot enough to start burning. We don't know how the next stage develops because it's turbulent and chaotic, but we're beginning to make some very interesting simulations of those stages. But once it explodes, it tends to make a very standard sort of event that's called a type 1A supernova.
And just to clarify, astrophysicists are colloquial in their use of burning. This is all fusion, not combustion.
That's right. Although I would quibble. I think we should be able to use the word combustion too.
Okay.
Because it's a process that is just like the chemical process, except it involves nuclear transmission, transmutations, rather than chemical transmutations.
Right.
So you can write out the same set of equations, solve the same set of equations. You just put in different coefficients for the rates at which things happen.
And when it came to starting to test these theoretical ideas, what were the best observational verifications that explosive nucleosynthesis actually happened in the way people were thinking about it?
I remember being at Caltech working with Willie Fowler as his postdoc, and one day going in and showing him a numerical calculation for explosive carbon burning, which produced the isotopic abundance pattern for neon, sodium, magnesium, and aluminum.
Well, all at once. You just,
all at once.
Yeah.
To relatively high accuracy for astronomy at the time, to a few percent.
Wow.
And the key elements of the calculation were to choose conditions that we thought were appropriate to an explosion in a star. And it just fell out.
Wow. And when you get a match across the periodic table like that, it's like an aha
it gets your
moment.
attention.
Yeah.
It gets your attention.
Right. And could the calculations be done to continue all the way up the periodic table to the rare
Yes.
metals?
Now
and so on?
we've essentially done the whole periodic table.
Okay. And just again in just order of magnitude terms, what are the physical conditions under which this occurs?
Different elements and different isotopes of those elements are sampling of different processes. And this was the thing that Al Cameron and Fred Hoyle, Willie Fowler, and Jeff and Margaret Burbidge did back in the 50s. They managed to identify the different processes. And since then, it's gradually gotten more and more refined as we have better estimates for the cross sections. We have better estimates for the stellar conditions. It's not converged yet, in my opinion, but we're getting very good compared to where we started from. So I think we now have a fairly good picture of how the elements come about. It's not a question of how they come about. It's exactly where and when they came about. So we're beginning to ask finer, detailed questions.
And these are conditions. Are they approximatable, or are they're in lab physics even momentarily?
Yes, at the National Ignition Facility, which is a very large laser or set of lasers at Livermore, California. They focus the laser on something about the size of the tip of your little finger, about a centimeter in size. And they're able, in fact, it's more like a tenth of a centimeter across. And they're able to reproduce conditions that are hotter than the center of the sun. They are as hot as the center of a red giant. That is helium burning.
Right.
This only happens for a millisecond.
Right.
But it can be reproduced in the laboratory.
Okay.
Which is amazing.
It is amazing. Well, and it's a whole new arm of the science that you can have some level of experimental verification of your ideas.
Yes.
So since people, think of these incredible stories of where the atoms that they're familiar with came from, obviously the heavy elements can be produced two different ways, but when someone's just looking at the gold ring on their finger, roughly what fraction of those atoms came
They came from a red giant star.
Okay, they came from a red giant.
Or more precisely, an asymptotic giant branch star with thermal pulsing.
Okay, so if they want to look around their everyday world for some supernova-produced atoms, what would they look for? Where would they look?
Well, one of the best, and I think the most spectacular, is an iron meteorite.
Okay.
An iron meteorite is basically the iron that was produced as unstable nickel
Mm-hmm.
and related isotopes in a supernova explosion itself.
Wow.
The composition, the detailed composition of the isotopes and the elemental combination in iron meteorites is a smoking gun.
Mm-hmm.
I mean, it's determined by nuclear physics.
Right.
So if you make stuff hot enough, that's what you get.
Mm-hmm. So it's kind of cool because people can buy an iron meteorite or a piece of one. It's a wonderful primordial solar system fragment, and it's telling a much earlier story.
A
too.
much earlier story of the very extreme conditions in a supernova.
Right. Now, back to 1As again. Obviously, cosmology is hanging in the balance here. So this is an unusual situation where something that's so extreme and explosive is so well regulated we can use it as a cosmological tool. How does that work?
We couldn't do it theoretically because we didn't have, still don't have enough information
Mm-hmm.
to predict with really great precision the conditions in the supernova. We understand them well, but only to a certain level.
Mm-hmm.
The precision comes from observation. There have been a number of efforts, particularly the people at Ceratololo, who have examined supernova in nearby galaxies and calibrated them very precisely.
Mm-hmm.
Because the systems obey a fairly simple set of physical laws, they have a fairly simple pattern of behavior. And although it's not as though each type 1A has the same luminosity, the ones that are brighter take more time, and the ones that are dimmer yet evolve more quickly, and they're done.
And is that general trend that I know is used to tighten up the relation for distance indicators? Is that understood?
That was in fact the paper I mentioned earlier that I did after the hike.
Okay.
Worked that out
Right.
theoretically.
Mm-hmm. So now in this situation where they're empirically these very powerful distance indicators out to the edge of the universe and to allow us to trace the expansion history, presumably it's still important to know that supernovae behave the same here and there and
Yes.
now and in the distant past. So do we have any concerns there, or are there issues still?
If we're reasonable people, we have concerns.
Because it's still the only direct/indirect evidence for dark energy, right? As far as I know, there's everything else is
Yes, the dark energy, dark matter we have from the rotational curves of galaxies.
right.
And Zwicky did that long before we really were able to use supernova as a yardstick. But yeah, you're right. Dark energy is pivotal.
So much in cosmology really does depend on that and trusting it and believing it. I presume that's a fair amount of impetus to understand them theoretically at the level where you're confident in the empirical relation.
Well, now, you're getting into an area where I like to make some sort of comment to the fact that, we've really done pretty well since we only have puny little primate brains to do
Right.
this with.
Right.
And when you start talking about cosmology,
Mm-hmm.
it would be very easy to make some essential error.
Mm-hmm.
And if you look at the history, well, we have made some errors. But it's amazing to me that we now do, in fact, understand cosmological things in a quantitative way. Not that we have solved all the problems. I don't believe we have. But I think it's just, we were very lucky to be living in this time
Right.
when we have discovered these things.
Right. And maybe in going the other way, in terms of being unlucky, we're just way overdue for a supernova in our galaxy. So absent that, since it's whatever, 1604 was it, Kepler's? last
That's
one?
right. But I consider myself exceedingly lucky that I wrote a dissertation 20 years before supernova 1987A
Right.
went off. Actually, 30 years, no, 20, 25, in which it was predicted that neutrinos would be emitted.
Mm-hmm.
And not only they would be emitted, but what their energies would be.
Mm-hmm.
And these were detected.
Yeah, so let's talk about that, because, well, in general, just let's talk about the role 1987A played in just affirming or pushing the field forward, and then neutrinos in particular, because it's very interesting. There was quite a lot of mass energy in neutrinos, and they arrived first, right? Slightly ahead of the.
That's right. They arrived slightly ahead of the light because the neutrinos could penetrate through the star.
Mm-hmm.
So when the core collapsed, the neutrinos set off, escaped the star,
Mm-hmm.
and the explosion had to go more slowly because it had to get out through all the plasma that was overlying the core.
Mm-hmm.
That took about an hour.
Right.
And then we saw the burst. So the optical detection was after the neutrino.
Mm-hmm. And the theory was, what theory you were involved in was sturdy enough to predict neutrino fluxes?
We were just really, really lucky. It turns out the weak interaction, although in many ways it's very messy, in this respect it was very lenient. If you simply knew that the weak interaction was basically the value that Fermi used when he did his Nobel Prize work on the beta decay rates, and you assume that it happened universally with particles
Right.
in the middle of the supernova, then you would immediately infer, and as the energy of the neutrinos is in about the right range. It was hard for, this didn't happen immediately, because it's hard for people to get their minds around the fact that these neutrinos, which were so weakly interacting in the supernova under the extreme conditions, were no longer weakly interacting,
Right.
but in fact interacted a lot, and it took them a while to escape the order of a second.
And how much sort of mass energy was being carried out with that wave?
About 10% of the rest mass of the neutron star.
Wow, that's pretty amazing. And it was just a handful of events, though, right? That the Japanese detected.
The total number of events, it depends on how you count them. And taking an optimistic point of view, there are about 24.
Okay. And is neutrino astronomy, just as a sort of aside on that, has neutrino astronomy progressed substantially? I mean, that was an incredible way to kickstart a field.
Yes, that's right. And the other thing that has been happening in parallel to that is the neutrinos from the sun have been detected.
Mm-hmm.
And the detection of those, in fact, gave us insight into the nature of the weak interaction that suggests that it is beyond the standard model, because the neutrinos have mass.
Right.
And originally they were thought to be massless.
Right.
They don't have very much mass, and they travel at almost the speed of light, which for supernova 1987A was an interesting point, because the Large Magellanic Cloud is very far away.
Mm-hmm.
So if they didn't travel at the speed of light, then the neutrinos would have been passed by
Right.
the photons,
Even though they got a little head start.
though they got a head start. And that allows you to place a limit on the mass of the neutrinos, and it's a small mass,
Right.
and which we worked out at the time. And it's if you want to be picky, they are not massless, but they're almost massless.
Right, which sort of implies...
They are very close. They travel at very close to the speed
Does
of
that
light.
imply some fine-tuning or some issue? Or
Well, we don't know.
Okay.
This is one of the issues in particle physics.
But it's, as people read about the Higgs, tying a neat bow on the standard model, it's worth remembering how incomplete the standard model is.
It's not quite. You could probably. Well, I don't know what the latest ideas are. I haven't been following that in the last few years, but I would suspect that there will probably be a variation on the standard model, which could handle. Or maybe I shouldn't call it the standard model, a variation on current theory in which we can handle the neutrino mass.
Mm-hmm.
The idea of supersymmetry, for example,
Right.
which seems to be a possibility according to the people at CERN.
Mm-hmm.
Maybe that will. Anyway, we live in interesting times.
Yeah.
I don't know the answer to that.
Right. So with 1987A in the rearview mirror and us being overdue for a Milky Way supernova, are there other aspects of theory, things you work on, where we'd really love, not too nearby an example, let's say not less than 10 light years or something.
Not too close. They're dangerous.
Be careful what you wish for. But are there must be a lot of, given the progress in the field, there must be a lot of things we could test really well with a 100 parsec supernova or something.
Yes.
So that would be a
That would
wonderful
be great.
time if
that
that
would be
happened.
great. If there's one in the galaxy, we will be able to not only detect the neutrinos, but detect them with such precision that we will be able to explore the inner details of the explosion.
Mm-hmm.
And we'll probably be able to pin down the gravitational wave emission
Mm-hmm.
as well. So not only would we have better observations of the explosion with telescopes.
You mean assuming LIGO's working or independent of LIGO?
Well, I'm assuming that there will be something working. If LIGO,
Mm-hmm.
if there were a core collapse in the galaxy, LIGO would see it
Yeah. Okay, anywhere.
anywhere.
Yeah, right.
Yeah.
Okay, so we are overdue, and that will be a wonderful time.
Yeah, and there are more things that we can observe it with now.
Right. Well, let's talk a little about the core collapse and what gets left behind from a supernova. And again, just in terms of timescales and physical situations, describe what core collapse is, because it's pretty extraordinary.
Well, this is how I earned my spurs as a theoretical astrophysicist.
Mm-hmm.
My thesis was on core collapse and neutrino emission.
Mm-hmm.
At Caltech, I and Kip Thorne co-edited a book by Zeldovich and Novikov. It was originally in Russian. Kip had it translated from Russian into non-scientific English.
Okay.
And then he and I had the task, a much harder task, of translating the non-scientific
Wow.
English back into scientific English.
Yeah.
That was hopefully up to the standard of the scientific Russian.
Mm-hmm. Wow.
So
I bet that took more than a year or
no, it only took a year.
Really?
We only had a year to do it.
Okay.
So that was a lot of work.
Mm-hmm.
However, it paid off because later, in 1973, at the International Astronomical Union in Warsaw,
Mm-hmm.
Zeldovich came. Now, this is the middle of the Cold War. So Zeldovich was surrounded by a lot of very sturdy guys in very ill-fitting suits, and you could never get in to talk to Zeldovich because there was always this crowd of males
Mm-hmm.
around him.
Were they worried about him defecting? Or just they wanted to buffer him from Western?
This comes out.
Okay.
This comes out. Bohdan Paczynski
Mm-hmm.
saw a way to solve this problem. He invited me to go to a mushroom picking picnic on the grounds of the Warsaw Observatory.
Okay.
He also independently invited Zeldovich.
Right.
The guys in the bad suits didn't seem to want to come.
They thought it was innocuous. They didn't figure this out.
They didn't figure this out. So I got to talk to Zeldovich.
Mm-hmm.
And it was great fun. We talked about the book and supernovae, and then I screwed up my courage, and I looked him in the eye, and I said, you know that these supernovae are a lot like atomic bombs. He got a big grin on his face, happy that I had asked it and made this point. He said, yes, I know. And of course, he and Sakharov were the two leading physicists who were involved in the second Soviet bomb.
Right.
The first Soviet bomb was the one that Klaus Fuchs had stolen the plans for.
Mm-hmm.
It was the Nagasaki bomb, the plutonium bomb.
Mm-hmm.
And it was interesting that Stalin did not trust his scientists. So he chose that the first Soviet bomb would be from the American plans.
Wow. Interesting. Yeah.
On the other hand, the second Soviet bomb was smaller and exploded with more power, and it was designed by Sakharov and Zeldovich. So, I think that in science, if you don't tell people the way to do something, they may very well just invent something far better than you knew.
Mm-hmm.
And that's what makes security with nuclear weapons such a difficult problem.
Right. And Zeldovich never, he would stay, did he stay part of the Soviet apparatus?
Yes.
He didn't leave, actually.
He didn't leave. He stayed part of the apparatus.
Whereas Sakharov obviously became.
Sakharov was, Zeldovich was not a rebel.
Mm-hmm. So back to the core collapse. What's going on in core collapse? Because some of the time scales are incredibly short. The bounce and so on. It's for such a large amount of material.
Yes.
It's kind
It takes about a second for an object the size of a white dwarf to shrink down by a factor of 100. And the conditions inside are like the conditions in the nucleus of an atom. And because of this enormous compression, the electrons, which get carried along for the ride,
Mm-hmm.
get compressed enormously. And that, in fact, is what causes the production of all the neutrinos.
So you just force beta decay to go backwards.
You force beta decay to go backwards because you're crunching the stuff. And it's being crunched because the gravitational field is so big.
Mm-hmm.
If, in fact, the mass is above about 2.5 solar masses, then the collapse can't stop, and it goes on to form a black hole. And that's what I tried to sort out in my thesis.
Now, you also must have known that the magnetic field is getting crunched too. How does that affect the calculations or the expectations of what happens? Because you've just also got phenomenal magnetic fields.
One would, there's a group of astrophysicists who think the magnetic field is a key part of what's going on. I don't, because of two instances. One, in the experiments with the NIF laser, in which we're making plasma at stellar conditions, not neutron star conditions, but at least at stellar conditions.
Right.
There are magnetic fields, there are strong magnetic fields, but they are sort of carried along for the ride. So although they make a lot of interesting phenomena, they're not the dominant thing. They're not the big part of the game.
Right.
And the same thing's true of the sun. On the surface of the sun, have these wonderful flares and incredible magnetohydrodynamic phenomena. But if you follow those magnetic field strengths down into the center of the sun, the magnetic fields become a small fraction of the energy. So again, it's kind of frosting on the cake.
Right.
Wonderful stuff.
Yeah, definitely.
But I think it's probably not the main game. Now, having said that, the part that we are most ignorant about is the coupling between rotation and magnetic fields. And we know that in some core collapse, rarely, but sort of 1% of the time, not only is there the collapse, but there's evidently a lot of angular momentum involved in the collapse. And the standard story then breaks down because of the rotation. As it collapses, it spins up. So there's a lot of rotational energy. And this apparently makes jets. The only way we've been able to figure out how that works is with magnetic fields. So it may be a little bit like a flare on the surface of the sun, qualitatively, in that a lot of energy is in this collapsing, rotating thing. Some of it gets transmitted into a collimated jet, and that's still a small part of the total energetics, but it's enormously larger than any other explosions we know.
Right, okay.
But we don't know how to do that story.
Right.
Because we don't even understand very well how the center of the sun got to its current rotational state.
Which is an amazing thing to be
Yes.
uncertain of at this
Yeah,
stage of
well,
our field.
I think that within the last 10 years it's become a lot clearer. But it's a very recent development.
Right. So you've partly answered this, but I want to finish by asking about, the questions things that not keep you up awake at night, but when you have your musing time and you think about an interesting puzzle or a big problem yet unsolved. I mean, this field is really mature compared to, when you started and the state of the theory and the computer. So what are the big questions remaining?
Well, we're just passing a threshold with regard to the computers. We now have enough computer power, just within the last decade, that we can calculate a volume of the star with sufficient resolution that we can actually see it become turbulent. Previously, there was so much numerical dissipation, so much numerical error in the systems, that we couldn't see the sort of turbulence that you can see in your bathtub. But now we're getting to the point where we can actually see something that looks like a patch of the surface of the sun.
Right.
Okay, that was the last 10 years. Now we're at the point where we can begin to do whole star calculations with enough resolution to see the turbulence. And one can calculate it with the magnetic fields as well. Whether or not we're really correctly imitating what stars do is another issue. And it's a very difficult one because you can always imagine, well, suppose I resolved it by another factor of 10. And that, by the way, would take, let's see, factor of 10, that would take about 10,000 more computers to do.
Okay.
Just to scale it up.
Right.
It would not necessarily behave the same way. Because we haven't done the experiment, we don't know what the answer is.
Right.
We can assert that it would behave the same way, but that's just a guess.
Right. So this is an exciting time then because of
So it's an exciting time. We can get part of the way there, but there's no free lunch. We still have to make some extrapolations, and we have to try to be as intelligent as we can to make sure that we're not making a silly extrapolation.
Mm-hmm.
Uh,
So let me ask one more question about the fundamental physics, because the understanding of these transient states of stellar evolution has informed a lot of fundamental physics. Now, when you're thinking about that, atomic nucleus density material, there must be some interesting, physical issues regarding that phenomenology and things we might want to wonder about and see if we can have any experimental indication of what are there any questions that interest
yes.
you as far as the state of that physical
Well,
state?
one of the very interesting questions, which we're beginning to get glimmerings of an answer, is the maximum stable mass for a neutron star.
Mm-hmm.
How big can a neutron star, how massive can a neutron star be and still not collapse to a black hole?
Right.
And the number is somewhere between 2 and 3.
Okay.
Now, there were theoretical reasons 40 years ago that suggested a similar number. So that's sort of interesting, maybe a little bit comforting that we're in the right ballpark,
Mm-hmm.
maybe a little bit disappointing that we're still using the same sort of numbers. But the difference is now we have some observational data which can be traced back to bear on the subject. And that, the idea of this thing that is 1.5 times as massive as the sun being just an enormous atomic nucleus,
Mm-hmm.
of which there are 10 to the 23 in a thimbleful of water.
Right.
That's an enormous range of scale.
Yeah. And it's not a homogeneous object, is it?
And it's not a homogeneous object.
Right.
And it may very well be that the magnetic fields do weird and wonderful things there too.
Mm-hmm.
Although again, I think the magnetic fields don't do so much in the center, but boy, they make for a very interesting afro on a otherwise bald head.
That's a nice way of putting it. Yeah. Okay. Well, there's plenty of flavor left in the chewing gum.
Yes,
even
that's
after
right.
40 or 50 years. Yeah.
Yes.
Okay.
And it's really been an amazing time, and I think we're very fortunate. We had the supernova 1987A,
Mm-hmm.
which is the closest supernova since the Kepler,
Mm-hmm.
and that's pretty lucky. In fact, if the supernova had been situated at the backside of the Magellanic Cloud, the neutrinos still wouldn't have gotten here. They'd still be in transit.
Oh, wow. Interesting.
Yeah.
Okay. Well, thanks a lot, Dave. Appreciate
Well,
it.
thank you, Chris.